have been solving differential equations like this. And I know that if it's f prime, if it's dy dx, just the same. You know, I can replace this with f prime, and I could find f. Okay? And we can find the general solution. Maybe instead of f equals the antiderivative, we'll have y equals the antiderivative. So go ahead and find the general solution, which will include a plus c, to that equation, differential equation. Y equals. What do we do to solve a differential equation? You just did it on your quiz. Well, maybe you did. Okay, sorry. If f prime of x equals 2x plus 3, solve the differential equation. What do? Take the antiderivative, please. Okay, so can we all do that with dy dx equals 2x plus 3? We get x squared plus 3x. What are you all forgetting? Plus c, thank you. Okay, great. This is the general solution. It has a plus c. You didn't remember the plus c's on your quiz. It'll be okay. But only for the first page. On the back page, if you forgot your plus c's, you did not solve the differential equation correctly. Because we know if you're given an initial condition, this is how you find c. If I plug in 1, I should get 2. It's really nice when I have this y equals format because I can just plug in 2 for y and 1 for x and find c. Okay, now what I want you to do, and you have a lot of space actually in this recall implicit differentiation, is draw x squared plus 3x minus 2. Now, without your calculator, who could tell me where the vertex is located? -2 is not where the vertex is located. I'm thinking about an x coordinate. This is a challenging problem. Use your knowledge of calculus to answer this question. Right idea, but wrong flipping. -3/2. Why do you say -3/2, Mr. Hotmeyer? And this is a very, very good thing that everybody should pay attention to. Why -3/2? No. Mr. Dorsey, do you know why? That's when the derivative is 0, right? Vertex is when the derivative is 0. If I plug in -3/2, I'll have a slope of 0. So let's just like focus our attention around -1.5. And now we kind of know that we're going to go down 2. It's not necessarily down exactly 2. So we'll just like pretend that this is our graph. And we know if I plug in -1.5, I have a tangent slope of 0. Go ahead and draw that tangent slope. That's dy dx when x is -1.5. And we know by plugging in these x values what these slope values are going to be. Go ahead and draw a bunch of tangent slopes for me. Now, is this graph the only graph whose derivative is 2x plus 3? Discuss with your neighbors if there are other graphs besides this graph whose derivative is 2x plus 3, and what would they look like? Go ahead, discuss, please. make your answers unnecessarily complicated just because you think this is a complicated class. It's not a complicated class. This stuff is easy. Don't just assume the answers have to do with ease, signs, or logs. Okay? We know because of this general solution that a parabola whose vertex is at -1.5 will have a derivative of 2x plus 3. Which means if I change c, if I put my parabola up here, doesn't matter. It's still a solution. So, 0 tangent slope, positive tangent slopes, negative slopes, we'd be able to see that. We know that if it was shifted downward, as long as it had this vertex and it had the same shape, we would be fine. I feel like I'm not getting observed. Mr. Bester. Silly kids doing stupid things. So if I shifted it down, it still would satisfy this differential equation. Now, going to have a slope of 0, positive slopes, negative slopes. Now, the reason why I'm doing this is because we have an alternate approach to being able to figure out what my solution, what my y equals solution would be without knowing how to take antiderivatives. We haven't talked about it until now because it wasn't necessary until now. If I just knew what the slopes had to be, if I just remove these graphs, and I just knew, hey, these are my slopes, we would be able to see, oh, the only type of graph that fits these slopes is some parabola. You can kind of see the parabola by looking at the slopes, right? Okay, good. Good. Keep that in your brain. That the slopes can show you the solution. All right. Now, these are boring. You just have x's. Let's kick it up a notch. We did not have only derivatives with x's. We remember we had derivatives with x's and y's, like this one. Well, we are going to go backwards with this derivative. We will find what y is equal to when dy dx is negative x over y, or any other type of derivative. Now recall where these derivatives of x's and y's come from. They come from derivatives of implicit equations. Remind yourself, how do you take the derivative of 3x squared plus 4y cubed equals 10? Go ahead, take the derivative, find what dy dx is this. What dy dx is for this. Good. Equals 0. Okay. The derivative of x is not dy dx. It's just 1. The derivative of 3x squared, when I took the derivative with respect to x, was 6x. The derivative of 4y cubed was not just 12y squared. It's 12y squared dy dx, because of our knowledge of the chain rule, equals 0. Okay, there's dy dx. It just showed up. What do I do now? Solve. Good. Solve for dy dx. So subtract the 6x divided by 12y squared. And I get negative x over 2y squared. Okay, cool. Our goal today, take this, go backwards. Okay? Now, for all of these differential equations that we've been doing in this unit, we've been saying like, hey, take the antiderivative, right? But how the heck do I take the antiderivative No, it's not arctangent. It's not e to the x, it's not log x, okay? So I don't know. Honestly. I don't know how to take the antiderivative of negative x over y. So what we're going to do is investigate this alternate approach to being able to visually see our solution. We know that if I can see the slopes, I can see the shape of my solution, okay? So we are going to investigate negative x over y by creating what is called a slope field. We already kind of created it on the first page with 2x plus 3. A slope field is a visual representation of your tangent slopes using dy dx. By looking at your tangent slopes, you should be able to see what y equals should look like. Let's take dy dx equals negative x over y. Again, I do not know how to take the antiderivative of negative x over y. What I will instead do is assume that I got a bunch of points on my solution. Let's just like assume 1, 1, or f of 1 equals 1 is like an initial condition. Let's just assume that. What I could do is say, okay, if 1, 1 is a solution, its tangent slope would be negative 1. Where did I get that? I got that from plugging it in here. And what I will do is sketch one of these tangent slopes, understanding that this is a negative slope. This would be like a positive slope going up and to the right. And at minimum, no matter what is going on, no matter what this graph looks like, whose derivative is negative x over y, it could look like this. You don't sketch this. It literally could look like this, but I know if it's going to have the point 1, 1, it's gotta have that tangent slope. That's information. It's not much, but it is. Put it in your box. Well, again, we didn't know anything else, so like the possibilities for what the shape of my graph are endless. But let's go ahead and find the slopes assuming these other points are there. For example, let's use the point 1, 0. I have negative 1 over 0. That is an undefined tangent slope. An undefined tangent slope is vertical. All of a sudden, I could have a bunch of different graphs here, but if I'm going to have this point, 1, 0, I know it's going to have a vertical tangent, and that vertical tangent is going to kind of push me into that point 1, 1, and all of a sudden I have a little bit more understanding of what the shape of my solution is. Well, let's continue to graph these slopes here and here and here and here. So you guys assume we have the point 0, 1, negative 1, 1, negative 1, 0, negative 1, negative 1. Plug it into dy dx and graph little tiny tangent slopes. Go ahead, do it for the other points. Very nice. Yep. What's the zero slope look like?
Undefined.
Undefined is vertical.
So it's just zero?
What's zero look like?
Zero, like this.
Horizontal.
Okay.
Yeah. Okay. 0, 1, the slope is 0. This is a horizontal tangent. Draw a horizontal tangent. Negative 1, 1, well, that'd be positive 1 over 1. I have a slope that's positive 1. Negative 1, 0, vertical. Negative 1 will end up being negative 1. 0, negative 1. 1, negative 1, end up being positive 1. Now, if I start out with this point, let's say I assume this point, my graph has to go up. And then it's going to probably lead me over here. And it's probably going to lead me over here. It's probably going to lead me over here. And all of a sudden, we kind of see a circle, but maybe I see like a hexagon or an octagon. Like, I'm not super certain. So that's why we can continue to do this for more and more points. This is what you just created. You created this part of it. You did that. Good job. Now the computer then continued to plug in more and more points. Now, Mr. Ballard, by looking at slopes, we could see the shape of our y equals solution. What is the shape that you see? A circle. So what do we see? We see a circle. So we think the antiderivative of this has to be some equation for a circle. Who remembers? We all took pre-calculus, right? Did you guys all take pre-calculus? I hope so. No. Good. If you're going to remember anything from pre-calculus, you should remember the unit circle. But does anybody remember from all of the conics work that you did? The general equation for a circle centered at 0, 0. Discuss. I think there's arctangent somewhere. I'm pretty sure. There's E and an arctangent. Yes, but the H and the K is what the center. Center is 0, 0, so H and K are 0. Who knows? Who's certain? Now, variable, r squared is a number, right? Right? I'm going to put a C. You produce this equation by looking at this slope field, right? Now notice, C is about the radius. Notice, I could have any circle with any radius, and it will fit in the slope field. This is similar, this is the same really, as the idea of I could have had any parabola so long as it's an x squared plus 2x plus c that fits in the 2x plus 3 slope field, right? There's an infinite amount of solutions here. Okay. Check to see if this is correct. You can take the derivative of this. Are you going to get this? Go ahead, check. Would it? Well, that's the question. Is this our solution? What's the derivative of a constant? Put your phone away too, Mr. Hotmeyer. That should not be on your desk. 0. Oh, that's important. That's important. Since this is a constant, its derivative is 0. I should get 2x plus 2y dy dx equals 0. You, my friends, visually solve that differential equation. So you didn't know how to take the antiderivative of negative x over y. You still found the solution. So these question marks turned into exclamation points. It's pretty cool. So does that mean we're never going to have to take the antiderivative of negative x over y? Nope. That'll be our primary goal of this class, is to actually figure out how to take the antiderivative of this. No, it's this lesson. But you are required to understand this alternate approach of visualizing your solution, okay? So let's work with these slope fields. Note, depending on the slope field, it might not just be a shift. Depending on where C is, your solutions could, follow here if it passes through 0, 0. But if my solution to this slope field passes through this point, you're going to have to follow this. Okay? But it's really just like connect the dots to see what your solution looks like. If I ask you, hey, here's a slope field, what would your solution to this differential equation, some dy dx, equals this slope field? I could ask you, what is the shape of your y equals solution that passes through the point 1, 1? Go ahead. You guys can do it. So circles fit the previous slope field. Parabolas fit the first slope field. What fits this slope field passing through the point 1, 1? No. So this is a good kind of like pause. We can see it's got to go like this and probably something like that. Now, do you know this equation? No, but at least you know what the shape's got to be, right? What is it? What is the equation? I don't know what the equation is, but I know this is the shape. Okay. Now there are sometimes where not only can you see the shape, but you're pretty certain you'll know what the solution is going to be. So here's an example of like how you're going to be assessed on understanding the slope field. Some dy dx creates this slope field. You are asked, what is a potential y equals solution? Is it sine x, cos x, x squared, 1/6 x cubed, or log x? Please don't shout it out, but think about it individually. And then check with your neighbors when you think you have an answer. Do this for me. Check with your neighbors. Mr. Alanis, draw something that fits in that slope field on Mr. Ballard's paper. Draw something that fits in that slope field.
Like a parabola. Up here, that one.
That one. This one fits. Does sine look like that? Does cosine look like that? Does x squared look like that? Does x cubed look like that? Yes. Not complicated. Don't just assume it's going to be sine or log x. That's what everybody goes to. It's like, it's got to be log. Pretty sure. This is a complicated class. All the answers are complicated. Okay? Go to your homework. Go to the second page. Look at this one on the top right. Draw something that fits. When you draw something that fits, you'll be able to understand and look below. You actually have like a matching system. You'll be able to know which of these y equals would be the solution to that differential equation. So I should be able to see it's got to look like this. That is sine. That's my solution. Now, what is the differential equation that produces that slope field? No, you're thinking about the antiderivative. If I know y, what's dy dx? Cosine. Okay? Kind of go about it the opposite way. I can see the solution, so I know the differential equation. You'll be asked to do that for all of 6. Find the y equals solution, and then what is the differential equation that produces that? I talk you through it in the video, which is an hour long. Yep, don't worry, you'll do it on Monday after the break. Okay, now that led us to the next part of what you're expected to do with these slope fields. The next part is, if I give you a slope field, can you determine which differential equation produces that slope field? Okay, if I give you a slope field, can you determine which differential equation produces that slope field? Here's my advice. Pick some points where you see obvious tangent slopes. Now, you don't see it on your graph, but it's on this graph. At x equals 0, there's a bunch of vertical tangents. So at the point 0, 1, dy dx has to be undefined. At the point 0, -1, dy dx has to be undefined. Which one of these will that occur for? Discuss with your neighbors. If I plug in 0 for x, I should get something that's undefined. Ms. Boyko, what's the right answer?
1 over x.
1 over x. Okay? That's easy, though, just at x's. This one's a little bit trickier. Now, my advice is to find slopes that are like obvious. And start with that and work with one of those points. What are some obvious slopes? I see some 1s, I see some 0s. Let's look at this point right there. That slope is 0. I know that. Now, it's not obvious that we're at the point 1, 1, but you can kind of see it's fallen on the y equals x axis. So if I plug in 1, 1, I better get 0. Mr. Alanis drew a hand turkey on his notes. All right, Mr. Alanis, let's answer this one. I'm just going to pick on you for the rest of the class. Don't look at it somebody else. If I plug in 1, 1, I will get a slope of 0. If I plug in 1, 1, this is the only one that will give me a slope of 0. Okay, those first two are easy. The next two are harder. Okay? Because many of these will give you what you're looking for if you plug in like 1, 1. So I'm going to just start a little column here. If I plug in 1, 1, my slope should be 0. Okay, that's 1 minus 1 over 1. That's 0. 1 minus 1, okay, that's 0. 1 minus 1, that's 0. 1 plus 1, okay. This is 2. This is 2. Okay, D and E are out. Give me another one. 2, 1? What's the slope at 2, 1? Yes. I like that idea. Now, the problem is, this is going from 0 to 3, and I have 1, 2, 3, 4, 5 tangent slopes. So I'm not certain that that's 2, 1. I am pretty certain that this is 1, 1, but I don't know. Let's give it a shot anyways. This is the right approach to these things. If I plug in 2, 1, I should get a slope of 1. Now, I see I get 4 minus 1, which is 2. I'll get 4 minus 1. Sorry. That's way off. 4 minus 1 divided by 2, which is 3/2. Okay, that's close to 1. This is 4 minus 1 over 1. That's 4. This is 4 minus 1. That's 3. I don't know, man. I'm not going to make any decisions off of that. Negative 1, 1? Okay, let's use negative 1, 1. Because negative 1, 1 looks like it's got a slope of 0. Let's try that. Okay, well, 1 minus 1 over, okay, well, this is 0. Okay, this is 0. Okay, this is 0. Oh, didn't help me. Not going to help me. No. Different approach. Okay? Because right now we can't distinguish the three of them. Why don't I pick something on one of the axes? Now I can't tell what the slopes are on the y-axis, but that actually is an indication of what the answer is going to be. Okay, that's one indication. So we know which one it is for some of us maybe not. So maybe we're just intimidated by the fact that we don't have any tangent slopes when x is 0. Maybe we'll look at a slope over here and a slope over here. If I plug in something like 3, 0, I know that my slope is positive. Let's just go with that. If I plug in negative 3, 0, I see that my slope needs to be negative. Okay. 9 minus 0 over 3, positive 3. That's good. 9 minus 0 over 0, that's undefined. That's not correct. 9 minus 0, 9. Okay, that's still good. At least we've eliminated B. If I plug in negative 3, I should get a negative slope. 9 minus 0 over negative 3, negative 3. This is already gone. 9 minus 0, 9. Whoa. Yes. Now you don't see the tangents. The other way you could have approached this is, oh, I don't have any tangents at x equals 0. When I plug in 0 for x, I better not have a tangent slope. If you plug in 0 for x, you're not going to have a tangent slope. It's undefined. It's either vertical, doesn't exist. So yes, that is the other approach. All right, you guys try this one. This is on the notes still. Don't try to solve. Instead, pick points to plug into this one, and then you should see those slopes on these. So like, one, slope should be 2. 1, slope should be 2. 1, 1, 1, 1, 1, 1. 1, negative 1, 0, 1, 1, 0. Really, if I picked the point 0, 1, I'd be able to see my solution right away. If I picked just the point 0, 1. Nice. At the point 0, 1, my slope should be 1. There's 0, 1, there's my slope of 1. Here's 0, 1, my slope is not 1. Here's 0, 1, well, I can tell that all the slopes are going to be 0. That's not right. Here, I can tell all the slopes are going to be 0. That's not right. That's it. Okay? Could have done other points, but if you did that one first, you got lucky. All right. Done with slope fields, done with this visual understanding of things. Let's now find our solution by going backwards, by anti-deriving. Now, we already know what the answer to this differential equation is. What is it, Mr. Gerard? Excellent. So this is our goal. I know this is my solution. I know this derivative is negative x over y. But how can I go about it by anti-deriving? Well, the key is you're not going to anti-derive negative x over y. But since dy over dx is not one thing that always has to stay by itself, you can actually multiply both sides by dx. Now, when I multiply both sides by dx, the dx is gone from that side. And I just have dy equals negative x over y dx. And you know what I'm going to do? I'm going to multiply both sides by y. I'll cancel over here, and I'll have y dy equals negative x dx. Could you take an integral and put it right here and be able to accomplish or evaluate the integral? Integral, antiderivative of x with respect to x. Could you put an integral right here? And though we haven't done this yet, the variables are the same. So since the variables are the same, you won't need a dy dx or anything. You won't need anything crazy. You'll just take the antiderivative of y like you would with x. So we're going to do that. This is called separation of variables. You can separate your variables, which means put your y's with dy and move your dx's to be with your x's. You are now set up to take the antiderivative of both sides. This is 1/2 y squared plus c. This is negative 1/2 x squared plus c. What are your instincts telling you to do right now?
Solve for y.
Well, to get what we're looking for, I want x squared plus y squared equals c. So it's like, let's combine our c's. Anybody thinking of like subtracting our c's? Now, a lot of people think when you subtract c, you're just going to get 0. They're gone. Not true. We do not know that this constant is necessarily the same as this constant. But we can subtract two constants together. What's a constant minus a constant? Just a constant. This is very important. Though we are used to putting plus c's always, in this situation, we will only need 1 plus c. Put it on the right side with your x's. Okay? Now, to put our answer in this form, we'll do a little bit of manipulation. I'll start by multiplying everything by 2. Now, when I multiply the left side by 2, I just get y squared. The right side, I get negative x squared. But now I have to think about 2 times c. This is very important. We can write 2c if we wanted to, or we could just like create a new c. 2 times c is still just a c. And to get our solution to be what we expect it to be, which we came up with visually, we can add x squared to both sides. There you go. We just found this solution using antiderivatives, just like we've been doing all the other differential equations. Pretty neat. Now, do we always want blank to a power plus blank to a power equals a constant? No. What you will be asked to do, going backwards implicitly, is actually solve for y. So this example I wanted to do just because we already knew what the solution is going to look like. For all of your other examples, you're going to have to solve for y. Solve for y, solve for y, and what we will find is that there will be some situations where solutions are not functions. If I solve this for y, I'd get y equals plus or minus root x squared negative x squared plus c. This is not a function, but we will be asked to have our solutions as functions, which means we will need either the positive half or the negative half, which we'll decide which one to pick based on our initial condition. We'll get to an example like that in the future, but instead, let's try something like this. Let's do this one, not using a slope field, but rather going backwards using separation of variables and antiderivatives. Step 1, get your y's with dy, move your dx to be with your x's. Get your y's with dy, move your dx to be with your x's. To do this, I multiply both sides by y squared because y squared is in the denominator. I'll multiply both sides by dx because dx is in the denominator. When you multiply, that'll cancel, that'll cancel. Okay? Next step, take the antiderivative of both sides, but you don't have to include plus c's on both sides. You can skip that step. You only need 1 plus c on the right side. So please take the antiderivative of both sides, but you only need 1 plus c on the right side. Here's your antiderivative rules. We know this is y to the negative second. Add 1, multiply by the reciprocal would be negative y to the negative first. And over there on the right side, I got x cubed plus c. Following? Oh my gosh, I have no idea why I did that. I'm thinking ahead. Gosh, I'm going to have to delete that. Yes, I am. All right, sorry. Multiply both sides by 3 because our goal is to solve for y. Know that 3 times c is just c. Now, something that we haven't had to worry about in the past solving differential equations that we can think about strategically now is when do you want to find c? Okay? If we solve for y, I have to cube root both sides. If I then plugged in 2 and 1, I would end up having to cube both sides anyways. So it's like I go forwards, but then I have to go backwards. Instead of finding c at the end, we can find c whenever we want. I think in my homework video, I always find c after solving for y because I thought it was like preferable. And sometimes it is, sometimes it's not. It's all dependent. You can find c whenever. That's just my lesson here. Plug in 2, you get 8 equals 3 plus c. It is very easy to find c on this step. But the only thing you have to be worried about is that you're not done until you've solved for y, because that is what it's expected of you to do. You can take both sides to the 1/3 power, or you can take the cube root of both sides. But your solution is not done until you solve for y. Oh, I don't know why I put 5. Why I didn't put 5. Okay? Now, we are going to be getting into free response problems. If you look at your homework, we will see our first types of free response problems last page of our homework. Okay? Your test that you will have in 3 Mondays, so not the Monday we return, but the Monday after that. You guys get a weekend to study. We'll have free response problems. There will be 3 free response problems, and they will be worth 40% of your test. Okay? Each free response problem is worth 9 points each. Okay? Each free response problem will have multiple parts. Typically, for these questions, 5 of the 9 points come from this, what we just did here. Okay? So now we get into partial credit. You guys should be encouraged by this. If you separate your variables correctly, you get 1 point. So you're 1 out of 5 or 1 out of 9. If you take the antiderivatives correctly, typically you'll get 1 point for each antiderivative. If you solve for y correctly, and if you find the correct c. 5 out of 9. That's not bad, right? And if you make one mistake, say you messed up this antiderivative, but you did solve for y correctly, and you found the correct c with your messed up antiderivative, you'll still get those 2 points. Are we intimidated by these free response questions? Please don't be. All right, let's do another one. And then we got one more that I have time to do. Let's please just work on separating our variables. Now, in this case, y's are in a numerator. I was already thinking ahead. To get the y's with dy, I'm going to have to divide by y squared. Now, I don't like to divide by y squared because I like to keep my y's and my dy separate. So I'm going to multiply by 1 over y squared. Are we comfortable with that being the same as dividing by y squared? I hope so. I'm also going to multiply by dx so that the dx's are gone from the left side and the y's are gone from the right side, giving me 1 over y squared dy equals x dx. Okay, now, take the antiderivative of both sides. When you do, you're going to have that negative y over y to the negative first. I was already thinking ahead there. We rewrite this as y to the negative second. We take the antiderivative. The right side, 1/2 x squared plus c. Following? When do we want to find c? I don't know. It looks like we're going to have to do some work to solve for y. So why don't we just find c now? Why don't we plug in -1 for y and 2 for x? It ends up being very, very simple if I do that. One equals 2 plus c. c equals -1. So I found c. I've rewritten my solution with c, but I'm still not done. Now, I'm just going to go ahead and tell you what I would recommend doing in this situation. And a lot of teachers don't teach this. I'm not sure why. But if you have fractions on both sides of an equation, which you always do, and let's say I want y to come up, flip both sides. Take the reciprocal, or 1 over both sides. You get -y, or y over -1, equals 1 over 1/2 x squared plus -1. You can then distribute that negative. When you do the homework, you'll encounter some problems where we will have to worry about our domain and have to worry about either the positive side of things or the negative side of things. So when you get there, just watch the video and make sure you understand why we don't want a plus or minus, why we want the plus or the minus. Do that on Monday. Have a great break. Thank you for being attentive on the Friday before Thanksgiving.